Today we are explaining the paper titled Video Generation Models are General-Purpose Vision Learners.
What is the central claim of this work?
The authors argue that a large text-to-video generator can be more than a machine for making clips. After the right post-training, its learned understanding of motion, geometry, objects, and language can become one model for many vision tasks.
Why is it a meaningful change from current computer vision systems?
Strong vision models already exist, but many are specialists. A depth model predicts distance, a segmentation model separates objects, and a pose model estimates body or camera geometry. Each often needs its own architecture, decoder, losses, and training recipe. Earlier unified systems also mostly work frame by frame. That leaves them without a native reason to learn how objects persist, move, interact, or obey physical constraints over time.
So generating a video forces a model to learn more than the appearance of one image?
Exactly. To generate a plausible sequence, the model has to connect appearance to time, where objects are, how they stay identifiable, and how their positions change. Because text-to-video models are prompted with language, they also begin with a built-in link between words and visual meaning. The proposed model is called GenSection. It starts from a pre-trained text-to-video diffusion backbone, then trains that backbone to answer perception requests such as depth, surface normals, segmentation, key points, and camera pose.
Diffusion generators normally refine noise through many steps. How can the same backbone answer a vision request quickly?
That is the key reformation. Standard diffusion generation begins with noisy video features and repeatedly denoises them, which is useful for creating diverse videos but too slow for precise perception. GenSection instead feeds in a clean latent representation of the input video, fixes the diffusion time at 0, and runs the transformer once. The original backbone was trained to predict the velocity between noise and a clean video representation. For perception, the authors negate that output before decoding it. Their intuition is that this makes the final transformer features line up better with the target video representation, so fine-tuning converges faster and performs better.
Does one shared model really handle outputs as different as a depth map and the list of key points?
The paper separates them into dense and sparse tasks. Dense outputs have a value at every pixel, such as depth, surface orientation, or a segmentation mask. GenSection stores those targets as kethgonal images. For a one-dimensional depth or mask, the value is repeated across channels. For surface normals, the 3 channels carry the 3 directions. Camera pose needs more than 3 numbers per pixel, so the authors encode it as a ray map. They pack ray origins and ray directions into different spatial regions of a kethgonal image. That preserves the single visual decoder instead of adding a camera-specific output head.
And what changes for a sparse output, where the answer is a few coordinates rather than an image?
For 2D and 3D key points, the model appends learnable tokens to the video features, one set per frame. A small prediction head reads those tokens as coordinates. This is a lightweight extension, but it is also the part that fits the original visual pre-training less naturally than image-like outputs do. The other practical challenge is supervision. To train all of these targets together, every video needs depth, normals, mask, and key points. Real datasets usually provide only some of those labels and at limited scale. The authors therefore generate predominantly synthetic videos, where each required label can be rendered automatically.
Synthetic data is convenient, but why should it transfer to real scenes?
The author's hypothesis is that the large video generator supplies broad visual priors before synthetic post-training begins. The synthetic data teaches the output format, while the pre-trained backbone already carries experience from large-scale video generation. The experiments test whether that combination survives the shift to real benchmarks. The evaluation spans normal estimation, depth, foreground and language-guided segmentation, 3D key points, and camera pose, across both image and video benchmarks. Except for the language-guided segmentation task, training uses synthetic data rather than the benchmark training sets.
What is the strongest comparison in the main results?
The important comparison is not just against one baseline. A single GenSection model is tested against separate state-of-the-art specialists. The authors report stronger surface normal estimates than normal crafter and Lotus do, and matching or better depth and camera pose results against systems such as depth anything 3, D4RT, and VGG. It also reports competitive soft foreground segmentation on video and image data, better understanding of complex language queries than segment anything 3 for expression referring segmentation, and stronger 3D key point prediction than the name-specialized comparisons. The evidence supports a generalist model that stays competitive across very different outputs.
Does the unified design improve every task simply by training them together?
No. The ablation study is more nuanced. Joint training consistently helps for ground segmentation, while language-guided segmentation stays nearly unchanged. Depth and camera pose can remain intact or regress depending on the benchmark. And 3D human key point estimation degrades substantially when trained jointly. The paper suggests two reasons. Coordinate regression tokens do not match the continuous pixel space format used in video pre-training. And new tokens trained from scratch can disturb the attention patterns that the backbone had already optimized. The broader lesson is to modify a pre-trained generator as little as possible when transferring it to perception.
How much does the video generative pre-training itself matter, rather than just the amount of data or model size?
On depth estimation, the authors fine-tuned the largest available VJ EPI and Video M.E version to models on the same data. Their video diffusion backbone performs better. A randomly initialized transformer barely learns in the layer transfer study, while performance rises as more pre-trained layers are transferred. That points to the pre-training objective, not merely scale, as an important source of the result. The same results also show preliminary scaling behavior performance generally improves as the model and fine-tuning data grow. More strikingly, the authors report depth performance comparable to leading G4RT and VGGT Omega models, with between 7 and 500 times less training data. The range varies by comparison.
A generator is usually slow.
The feed-forward model removes the standard 50-step diffusion loop. On the reported TPU setup, the 1.3 billion parameter model processes an 81-frame video in 5.92 seconds, or 13.6 frames per second. The 14 billion model takes 10.03 seconds, or 8 frames per second. Those figures include substantial memory use. Finally, the authors look beyond the intended task. A model trained on synthetic clips containing one object can segment multiple objects in real videos without additional training. And although training videos depict humans, the model produces useful outputs for animals and anthropomorphic characters as well.
So the generalization is not only from synthetic scenes to real scenes, but also from one training category to unseen articulated categories.
Yes, those examples do not prove that every visual task transfers perfectly, but they support the paper's central intuition. A video generator has learned reusable structure that is broader than the synthetic labels used during post-training. The takeaway is that GenSuction turns a text-to-video diffusion model into a single-pass, instruction-steered vision system. Its shared representation is competitive with specialists across many tasks, learns efficiently from synthetic supervision, and transfers beyond its training domain. Its uneven joint training results also show that a truly general vision model still needs better ways to handle sparse structured outputs, without disrupting the pre-trained backbone.
That makes the contribution clear. The video generator is being reused as a general perception backbone, not just as a video synthesizer.
That wraps up this paper explanation.